been muted this whole entire time. I suck. So I was just looking up chitin and looking up chitinous and chitin, and the reason I'm writing is how to say chitin. This guy here came from Doctor Who, and I was just saying that's how I remember how to pronounce it all the time, is because of that little poem that somebody wrote. Anyway, okay. So I read the first paragraph. The cavern is large, but it has a very low ceiling, restricting your motion to 2 dimensions. The shape of the cavern resembles a square. A quick scan of the chitin density produces a map of risk level throughout the cave. Your puzzle input. For example, blah. No, 10 by 10, I imagine our input is bigger. You start at the top left position. Your destination is the bottom right position, and you cannot move diagonally. Okay, that's handy. The number at each position is its risk level. To determine the total risk of an entire path, add up the risk levels of each position you enter. That is, don't count the risk level of your starting position unless you enter it. Leaving it adds no risk to your total. Your goal is to find the path with the lowest total risk. Okay, so this is basically a shortest path algorithm where our cost of going from one node to the other is going there. So this costs, we enter here for 1. This costs 1 to go this way. This costs 1 to go that way. This costs 2 to go that way. And this costs 3 to go that way. And it's been ages since I implemented a shortest path. We could do depth first search. We've done that a couple of times now, but I imagine our puzzle, our puzzle input is quite large, and depth first search would probably take eons. All right, let's save our input. Oops, day15.txt. And let's save our test input here. Inputs test day 15. All right, save that. So I think what we need to do is look up what was his name? Dijkstra. Dijkstra's shortest path algorithm. Because I forget how to do that off the top of my head. There's a Wikipedia article on it. Let's see how bad this looks. Oh, this doesn't look too bad. We can do this, right? Okay, I'm going to first see if I can remember how to use this. Use create utils read file and say let lines equals read file test inputs test day 15. See, I'm doing it by hand today, and see if I even got it right. I did. Okay, good. So we're going to look at this algorithm here. Create vertex set q for each vertex v in graph. We'll set a distance previous, and we'll add the vertex to q. Then we set the distance of source to 0. So while q is not empty, we're actually gonna, because we need to add in that first one, right? And I don't know how big the first one is in the input, puzzle input. Let's take a look here. Oh, it's 1 again. So I would have an off by 1 error if I didn't count that. Because the cost of getting to this node is 1. Whereas in Dijkstra's algorithm, it's 0 cost to the source. So we'll just set that to the first node. All right. While q is not empty, we're going to grab a vertex u in q that has the shortest distance, the shortest current value. Okay, and first time through the loop, it's going to be the source. We remove u from q, and then for each neighbor of u, calling it v, still in q, we grab this alt. Distance is going to be the distance that we currently have gone, plus the length from u to v. And the length from u to v is just going to be the cost of getting, like the length from 6 here to 5 here is going to cost 5. To get from this location to here costs 5. So that's how we'll implement that part of it. if the alternate distance, if the alt is less than the distance of v, which starts at infinity, right? Then we're going to set that to the alt. And then previous of v is going to be u. And what the previouses are for is this part of Dijkstra. When we want to actually figure out what the path is, we actually start at the target, our target location, and then walk backwards on previouses. This will give us our previous shortest, and then we'll walk backwards from there and print out the path. And actually all we need to do in our case is just add up the paths. All right. Well, like I said, it's been a very long time since I implemented Dijkstra, so let's see if we can get this close to correct. Let's start by defining some data structures. How are we going to store all these things? Because each vertex is going to have an XY coordinate. Right, we're going to have each one of these guys so that we can... Then the reason I want to do that is because we need to get the neighbors, right? The way to calculate neighbors is by doing XY stuff. We could do... Well, let's start by creating a distance array or distance hash set, because we're going to be looking these things up by vertex ID. So is this going to be a hash set from a point to distance is just going to be a value? And then we're going to do the same thing for previous, but previous goes, instead of infinity, it's going to be undefined. So is this an option usize? I think so. And then our Q array, or Q set, is going to just be a list of all the vectors, all the vertices and their costs. And the costs would just be U sizes. All right, now we need to initialize all of these. So each vertex in the graph, and the graph is basically in lines. So we're going to loop over lines and set all these things up. So let mut y is 0 for L in lines. Let mut x is 0 for D in L.chars. What did I call it? D for C in L.chars, because we're getting a character at a time. And now we have an XY coordinate that we're going to set dist of insert XY is equal to infinity. Infinity in this case is just going to be the cost of the entire graph. What's U size max? We can just set it to U size max. Rust U size max. Yeah, standard U size max. Okay. That's going to be our infinity. That'll be large enough. And then in prev, oh, what do I do? Equal sign. Like that. I'm looking at this thing here. Okay. Prev insert xy is none, right? It's undefined. And then add v to q, so now we get a q set insert xy. And it's going to be the cost as u8, or as u size minus 0 as u size. So that'll be the cost of getting to that location. So that's the first 8 lines. And now we want to do line 9, which is dist entry 0, 0, or default, because we want to get it. What is it? Get mute? Like this, and then unwrap, star, and then we're going to set that to 0. So that's line 9. So now while Q is not empty, while not Q set is empty, what are we going to do? We're going to find the vertex in Q with a minimum distance of U. So we're going to loop over every entry in dist and find the smallest one, which should be 0, 0 to start out with. That's very inefficient, right? We're doing O of n lookup. We should be able to just do an O of 1 lookup if we can. But it has to be in Q. So for, let's say, k in qset.keys, and then we're going to find the smallest one. Let smallest equals standard usize max. So smallest is infinity if dist.get, all of these should be in, dist. So we should be able to just do an unwrap is less than smallest. Let's just say let dist u is equal to dist get on of key dot unwrap, and then we can say dist u is less than smallest, then smallest is dist u, and we want to actually save the key too because we need to remove it from Q, so we have to save that here. Let found is it's an I32 of 0, 0. We're going to find one. So we remove 0, 0. So now we're going to save it. Found is equal to key. And do that. And then we're going to say remove u from Q. So we're going to say qset.remove found. We probably have to do that, right? And now we're going to do this part here. For each neighbor of v of u still in Q. So I think we did this one time before. Const ders is a slice of I32, 4, right? Because we're only doing the cardinal directions. And this is going to be, let's go east first, which is add 1 to x, 0 to y. South is 0 on x, 1 to y. Then west is -1 for x and 0 for y. And then north. And the reason I'm doing east-south first is because that's the general direction we want to head. And then north is going to be 0 to x and add -1 to y. And it would be great if I could check this. Let's see what blows up. What do we got? Oh, I don't have hash set. Use standard utils, not collections, hash set. Still doesn't like that. Prev. Oh, I called it dist again. Expected array of 4 elements. And what did he get? Found a reference. Oh, do I have to put a reference in front of here? Expected U size found struct random state. What? Why is it expecting struct U size? Expected due to this. Oh, hash set. I want hash map. I saw this create vertex set and I was thinking sets this whole time. Okay. That was dumb. And we have to change these to hash maps as well. Okay. It doesn't like that. It's not iterable. Remove that. Okay. Okay, do that. And expected tuple. So this has to be dereferenced. There. Okay, so that checks. now we have the ders. Right, we'll loop over each one of the ders for D in ders, and we'll see if, so let new x is equal to, let's see, it's found dot 0 plus D dot 0, and let new y is found dot 1 plus D dot 1. I guess I could have done that in one let statement. Let's do that. And y, this, comma, that. There, that's clean. Okay, so now we're going to see each neighbor of v of u, which what we're doing here is going around each one of the, this is u, found is u. So we're going to go to each one of the neighbors of u, and we have to see if it's still in Q. If Q set contains an x and y. I wonder if I should have just not destructured that. Let's see if we need it again. Now we're going to set alt is equal to the distance that's found at u, and we know u has a distance, and we are actually grabbed it its smallest. Right, its smallest plus the length, which is going to be whatever's in there. Q set get. Yeah, maybe we don't destructure this. We'll call it V because this is what Dijkstra calls it. Get V, unwrap. And then we say if alt is less than distance of V, get V, unwrap. Then distance dist get mute of V, unwrap, equals alt, and prev get mute V, unwrap, is sum V. And we defined prev as option. Oh, I said option u size. This is actually an option I32, I32. Right, we're storing the vertices in there. Okay, so that's all of that. Does that check? It does not. We don't have it contains. Oh, okay. We can fix all of those ampersand V's. Contains key, I think is what it is. And we need to put ampersand there too. And there. We put ampersands everywhere. Expected u size, found u size. Hit F1 again. Okay, that checks. So far we've gotten most of Dijkstra done. Now we have this dist and prev array, and we want to start at the target, which is our width and height, -1. So let me just print out, do we have something at that location? This is, so let's say u is target, prev of u, target is this, and dist of target is this. And we will say prev of, for their test data, we're just going to 9,9. And dist 9,9. One more. Okay. Does that check? Can't do that. Prev has type hash map, blah, blah, blah. Oh, get. Expected, okay, need ampersands for those guys as well. Okay, so let's run that and see if Dijkstra comes up with anything. Okay, that's not a good sign. Oh, wait a minute, why is that? Oh, this is why, because I didn't do this right. I was reinserting every location everywhere. So this x plus equals 1. y plus equals 1. And I would not have been able to figure that out for a while if it hadn't been for cargo. And I missed the warnings, didn't I? All right. So our previous target is some 99 and distance target is 40. So the distance is, we got that correct, right? And that was 40 down there. I remember reading the 40. This is worrying only because it should have been the previous thing to go to. Right? We started our target and then this says if previous view is undefined, is defined, so 99 it is, while u is defined, and it is, then insert u at the beginning of s and then u is prev u, and then this will end up going to the same location each time, which is not good. So I must have messed up something here in setting prev. Oh, prev is u, not v. Okay, thank goodness for that. But we did get the right answer, right? Because we did calculate the distance to the end, and that was the key. But let me make sure at least I got the Dijkstra algorithm correct. And this is supposed to be found. Yeah, 9, 8. So now we step back from 9, 9 to 9 over and then 8 down. That's correct. And I think we could walk our way all the way back to the front if we need to. But we got the 40, which is what we needed to find. So let's run this with our real input and see what Dijkstra tells us. Oh, I forgot to move it. All right. Let's quit out of that and run that. Oh, so this is a problem. This is taking a very, very long time. And I killed the NVIM? I thought I was killing just this guy. All right. So this is a problem. We have some sort of a, let's take a look at the algorithm again. Maybe I messed something else up. Oh, I just saw this. If we're only interested in the shortest path between vertices, source and target, we can terminate the search after line 15 if u equals target. Where's line 15? So before we even go into the for loop here, we can stop if found equals target. We might want to set this. If found.0 equals width minus 1 and found.1 equals height minus 1, then break from the while loop. Oh, I didn't set those. Let's set those up here. Let width equals lines of 0 dot len. Let height equals lines dot len. So now those are set, and we're going to switch back to our test data. Oh, as I32. Let's run that, see if we still get 40. And we still get 9, 8. Oh, okay, so that still worked, and we still got 40. Okay. So now I'm going to change this back to input, save it, and I'm going to run it here so I can kill it if I need to, cargo line. Really? Okay, let's quit out of NVIM. Cargo run. No, it's still taking a very long time. Dang. Let's try it in release mode and see if that at least gives us an answer. But if this is taking forever, I can't imagine what part 2 is going to bring. We got an answer of 71? And that looks wrong. 71 looks too small. Inputs, input, day 15. It should be huge. Am I doing this wrong here? Println found is this. And this should be width -1, height -1, right? Oh, that's why. Okay, so maybe we actually got a real answer, but I just hard-coded the 9 nines in there. So width -1, height -1. We'll do that here. Oops, this should be width. Okay, so maybe we're there. Maybe we're there. Let's see if we're there. Oh, I forgot to run it as, let's run it over here. Documents, dev, AOC, cargo run, release. I don't like the fact that we have to do release runs to get it to run in reasonable time. This is still going. All right, 685. I'll buy that. I'll buy 685. And that's the right answer. Okay, and this is still running? Oh no, it finished and it got 685, but it took 32 seconds. And this took a second and a half, but we had to run it optimized, which is makes me sad and makes me nervous about part 2. Okay, so let's check this in. Oh, yeah. Okay, let's do that. I like that. So for y, comma, l in lines dot enumerate. And we did this also for our roguelike. And that way we won't forget to increment x and y, because we don't need to. Oh, lines iter enumerate? Is that what it said? Into iter. Oh, now each one of those is wrong. Okay. As I32, as I32, as I32, and so on and so on. Okay. Let's check in with Clippy. Clippy likes it. Git add source and inputs. Git commit -m day 15 part 1. Get that up there. And now what's part 2? I'm nervous. Now that you know how to find the low risk paths in the cave, you can try to find your way out. The entire cave is actually 5 times larger in both dimensions than you thought. The area you originally scanned is just one tile in a 5x5 tile area that forms the full map. The original map tile repeats to the right and downward. Each time the tile repeats to the right and downward, all of its risk levels are 1 higher than the tile immediately up or left of it. What? However, risk levels above 9 wrap back to 1. What? So if your original map had some position with a risk level of 9, then that same position on each of the 25 total tiles would be as follows. Each single digit above corresponds to the example position with a value of 8 on the top left tile. Because the full map is actually 5 times larger in both dimensions, that position appears a total 25 times. Once in each duplicated tile with the values shown above. Here's the full 5 times as large version of the first example above with the original map in the top left corner highlighted. Equipped with the full map, you can now find a path from the top left corner to the bottom right corner with the lowest total risk. The total risk of this path is 315. The starting position is still never entered, so the risk is not counted. Oh, starting position is never entered. Okay. I missed that the first time for whatever reason. But we came up with the right answer because Dijkstra helped. But if we're running, how long did that take, by the way? Oh, because it had to compile. How long does it take without compiling? Oh, it's still compiling. It takes, okay. Oh yeah, I'm looking completion time, not this thing here. All right, it still takes 1.5 seconds for a single tile. Are there shortcuts we can take? And then we're gonna have to increase this in every dimension? Well, I know how to do that, right? I mean, this is just then adding, looping over here for I in 1.6, right? Because it's 5 times larger, and then we just multiply each value. We multiply this value, and multiply this value. X is I32 becomes each one of those times I. Because it's 5 times in each dimension. Oh my God. Okay. I'll start this, but I don't think I'm going to be able to finish it. And I don't want to mess up my part 1. And also part 1 takes too long. Because this is, what's the size of this thing? Let me put the 15. So this is, it's 100 by 100. So we're talking, and that took 1.5 seconds to search through shortest path using Dijkstra. So making it 5 times larger is going to make it take, what, 30 seconds in release mode? Maybe? And that's if we set up our thing correctly. All right, let's switch back to our test input. And unfortunately, what's happening here is that we're creating this and then modifying it. And I thought, maybe we could just do extra stuff down here for part 2. But no, we need to create a brand new QSet dist and prev for the 5 times larger thing. So, oops. So we're going to do, we're going to split this up here and grab up, this will be like part 1 data and then part 2 data. And then we just implement this algorithm each for part 1 and part 2, passing in the width and the height. So we're going to create a function called build part 1. Oh, and it has to return all of this stuff. So we're going to create a struct called Dijkstra, and it's going to have these things in it, plus a width and a height. And I'm using I32s for these guys because. So those are those. We change these to oh, no, we change this to this. this, and this, and then all we'll do is create a struct of this from build part 1. We'll take a lines, which is a string, and return a Dijkstra. And then we will say dijk stra width, height, dist, prev. Oop, I left those things in there, qset. I left the mutes in here. Let me change those. Okay. And then that's okay, that's build part 1. Oops. Let's 2, 3, 4, 5. Let's put that down here at the bottom. Now I should be able to say build part 1. Let mod dijk stra equals build part 1 of lines. And then we're going to create a new function here. Dijk stra search. And we're going to take in we got to make it short named. dijk di is going to be a mut dijk stra, and it's going to return a usize, I think. Is that what I have here? Usizes, right? Yep. Okay, and so instead of println this, we're going to just say return dist get width -1, height -1, unwrap. And if it blows up, it blows up. And I mistyped width, and then we have to put a di in front of everything here. That. Dir stays the same. That goes to here. Qset goes here. That. Our width and height. And that. And what did we miss? Unclosed delimiter. Oh, yeah, I never finished doing this. Okay, so println day 15, part 1 is this. Oh, stop that. dijk stra search of stra. Like that. And this is di width and di height. And we have to pass in lines like that. And that's saying types different mutability. And we still have an error. What's this? What are we returning? Oh, found the usize, found usize. Okay, star. Done. All right, so for our test input, this should still generate the same 40 value. And it does. And for our input value, we're going to run this release. And it still generates 685. Okay, that's good, although it takes forever. Okay, so now that we have build part 1, we're going to do build part 2. And we'll do the same thing with lines here. And now we're going to just do, this is going to be very similar. So build part 2. Lines is going to take a slice of strings and return a Dijkstra. But now, instead of just looping over these things and creating those, we're going to actually have to multiply these out and then add. We have to figure out how we're going to add 1 as we go along to the x's, and then we're going to add 1 as we go along to. Is this just 1 plus 1? I think it is. So we just add x plus y and then wrap and just do a mod 10 on it. So that shouldn't be too bad. right? So for in, oh no, we have to, we need the value 1.6. I'll say 1.d equals 5 to make it clear we're doing multiplication from 1 to 5. And then what I'll do is we'll just print out this array after part 2 and see if we got it close to being correct. So this has to be mul times stop, right? That way it's 1 times that and 1 times that, or 2 times that. Oh, that's not gonna do the trick. We have to do it multiplying x and multiplying y, right? Otherwise this is just going to create the diagonals. For x mul in 1 dot equals 5, for y mul in 1 dot equals 5. So this will be x mul times x and y mul times y. And we do the same thing here. X mul times and y mul times. Okay. So that should give us our 25 by 25. Or sorry, our 5 by 5, which is total 25. And then we need to actually change this. Right, we're no longer setting it to be this value. Why did I go back? Stop that. We're going to be setting it to plus x mul minus 1 plus y mul minus 1, and all of that gets modded by 10. Oh no, not 10. We don't wrap around to 0, we wrap around to 1. Let val equals c as u size minus 0 as u size plus x mul minus 1 plus y mul minus 1. God. You can tell I'm getting starting to get really annoyed when I hit that thing too many times. Okay. Semicolon. All right. So then if while risk levels 9 wrap back around to 1. So we never have a risk value of 0, which means 9, yeah, so we're going to just subtract. And so we're only going to add 5. So we can just say if val is greater than 9, then val equals, minus equals 9. Right, and that'll wrap it around. Okay. And we have to mud it. Okay. I think this will generate this, but what we're going to do is we're going to print this out after we generate it. So we build part 2. Let's see if this even checks. Nope. Why did you wrong? Expected U size. Oh, but these are I30. Oh. Oh, but we can't subtract. Sure we can. Found I32. It's treating x mul and y mul as I32s. Oh, because of that. So we can say as U size. And it shouldn't go negative because we start at 1. Okay. Now we have 2 warnings because we're not actually using the result here, and let's use the result. For y in 0 dot dot extra width, height for x in 0 dot dot dij extra. I shouldn't have called it that. Width. We're going to say print bang the number at xy unwrap, and then println here, just like that. And we still have our test input. Oh, dijk extra. Okay, and we still have our test input. No, we don't. Let's change back to test input, and what we do is dump this out here. And it didn't work. Oh, because I have to change the width and the height. But that actually that was wrong, right? This is completely wrong. We should have seen our standard thing here, and we don't. 956. Then it says 13, but then it goes. No, there's a 7 there, but that could just be a coincidence. The last line is kind of correct. We see 944,581. Okay, so what did we do wrong? And it seems, yeah, so C is U size, which is going to be the 1, minus 0 is U size, so I'll give us a 1, plus X mol is U size minus 1, which should be 0, and that should insert at 1 times X and 1 times Y the value. All right. Let's figure this out. We can print every one, but it's going to be very big. Y32, I got to do it. Y mol times. So Y as I32 and the val. Okay, that'll be very big, but let's see what it shows us. 1, 2, 3, 4, 5, and it's hitting 0, 0 every single time. Oh, yeah, because I'm an idiot. So the X position is equal to X mol times the width. Right, and that's where we want to go 0 to 5. X mol times the width. So X pos is X mol times the width plus X, and let Y pos equals Y mol times the height plus Y. And then we can just say X pos and Y pos. X pos and Y pos. That can stay the same. This gets X pos and Y pos, and X pos, Y pos. All right. That doesn't check because, yeah, expected I32 for U size. I32, I32. All right. And it panicked. Attempt to subtract with overflow on line 99. That's a shame. Oh, yeah. So now we don't need to subtract 1 here. mess that up. Okay. And so 2, 3, 4, 6. Sorry, this should be 3, 4, 5, 6. Is that 0, 0 is 1. 0, 10 is 2. Okay, so maybe this is working. Let's print out the full width height. Times 5. Okay, I have to say it now. Is height times 5. And run that, and that should dump out the full thing. We ended with 3, 3, 4, 7, 9. That looks like it's working. The end of the top one here is, this is very big. It's annoying. Here it is. 95286. That worked. The front is 11637, and the bottom left is 6755. Okay, so we've generated the test data correctly. So I'm going to assume that we also generated that we will also generate. Here's my main, right here. Yeah. Here. Okay, so we don't need to print this out anymore. I'll just save it in case we need it later. So, ModProg, hi, how are you? Good to see you. Yes, I'm implementing Dijkstra. I'm basically going through here, but Dijkstra is proving very, very slow. So I'm worried that this is not the right approach. I ran it on our test input, and I had to compile it with optimizations turned on, and it still took a second and a half to find a path. So this should check. Oh, we still have 2 warnings. Oh, because we're not actually solving it. If you have a hint for me saying there's a better algorithm or a faster algorithm, please let me know so I don't waste all my time doing this. All right, let's try running this. I'm running outside of the thing in case it's taking forever. 315, so that came up with the right answer. Yeah, and my implementation of Dijkstra is just following, what's on the Wikipedia page. So who knows if that's right? And who knows if this is the most efficient implementation of Dijkstra. But it's the one I did. So let's try it with the actual input and see if it takes less than... Not sure if A* might be faster, but on grids there also might be better. Yeah, I've never done A*. I've done Dijkstra before, so that's why I jumped for that. But I haven't done A* ever. But let's see. I mean, if we have to fall back to A*, then we have to fall back to A*. Yeah. This is going to be painful. All right. Well, while that's running, let's look up A*. And see how hard this is. Yeah, I wish I didn't have it like this. Let's pull this out like this, and we can look at it this way. All right, this doesn't look too bad. And we only need reconstruct path if we need the path, but we don't actually need the path. We just need the length. All right. This is a set of discovered nodes that may need to be re-expanded. Only the start node is known. For node n came from n is the node immediately preceding it on the cheapest path. No, it's still running. Yeah, I've got a feeling Eric deliberately designed this that Dijkstra is too slow. You can look for grid-specific algorithms. Yeah, that's a good point. And I mean, this A* is similar to Dijkstra, right? We're almost there. Except we have the F score and G score. Open set is empty, but goal is never reached. Yeah, and then say if current is goal, then we can just return the total cost of where we came from. All right. Grid search. And this is in Python. I wonder, maybe we just fall back to using a crate. That would be bad. Rust crate A star. I mean, this is not the way to do advent of code, right? By having somebody else implement the code for you. We would have to learn how to. There's the breadth first search. Oh, that's just the algorithm. Okay. I was hoping it would give an example of how to use A star. That should be in the code. This is still running, right? Still running? Okay. Documentation repository. Source. Directed A star. Breadth first, Dijkstra, Edmonds. Strongly connected, topological sort. A good heuristic could speed things up. Yeah. Right, if there was some way to trim. And I don't want to look at the Reddit because I don't want to see how other people did it. I just want to see if I can do it. But this might be one where I hit the brick wall. A star bag. Oh, no, only numbers in range. Yeah, but I don't know if you'd. Yeah, so maybe, I don't know, maybe there's a way to trim, as we're doing a search, we can say, oh, this path is going to be too long, so let's abort that and look somewhere else. But I don't know how to do that with Dijkstra. Yeah. And what is N here? What type is N? I'm looking here in this A star code to see how this gets used. So we have a whole bunch of different types. Oh, I see. So we pass in the start node, which can be this. And then we have successors. This is how you find the successors. And the heuristic is this is having just the distance, but for us it's going to be the cost of getting from one location to another, and then success is just hitting the right. A star has a heuristic, yeah. So did you do ModProc? Did you do this one? Oh, hi Refsa. I didn't see your question there. Are you using a binary heap for the open set? I am not. I'm just using a hash map. So we have the Q set that's in Dijkstra, and then distance and prev, and they're all hash maps. You didn't do it, Mod? Okay. We'll figure something out here. I'm sure we will. Well, actually, I'm almost out of time. Dang. I didn't realize how late it was. Yeah, I might have to go away and think about this, and then maybe tomorrow if day 16 goes pretty quickly, then we can circle back to day 15. But this, or I can just leave this running all day. But I think Eric designed this such that this is exponential time, right? So it's probably going to take years to complete. But I'll leave it running in any case. All right, so I will, let's see if we can learn how A star works. We were looking at that on Wikipedia before. So we have a start, a goal, and an H. If it came from, for node N, came from N is the node immediately preceding it on the cheapest path from the start to N currently known, and starts out as an empty map. So G-score becomes a map with default value of infinity. So it's similar to Dijkstra again, and we start with the starting point as cost 0, again similar to Dijkstra. Now we have an F-score, which is different. And F-score start is equal to H of start. And what's H of start? H estimates the cost to reach the goal from N. Oh, how do we do that? How do you estimate how costly it will be to get to the goal from N? I mean, you could just set it to max. Oh, that's the heuristic. To trim that down until you get a good way to search on that. I mean, I guess you could just say it's going to be, maybe 9 times the width plus 9 times the height is the approximate cost for that location. Or 9 times the Manhattan distance from the current location to the goal, right? And that's only if we get a straight line and everything's on 9 in that way, I guess. All right, so while open set is not empty, so it's going to start out with start, so it won't be empty initially. The current is the node in the open set having the lowest F-score value. Right, so that's going to be whatever our heuristic is. If current is the goal, then we're done. We remove the current. That's a heuristic that makes A star faster. Okay, thank you, ModProg. So maybe we can do this. Unfortunately, I'm gonna have to flip back and forth a lot. So let's do. Let's rename this instead of calling it Dijkstra. What can we call it? So we're gonna actually need a different. So we'll do struct A star. Because we still need the width and height, but we need our open set, our came from, G-score, and F-score. Is there anything else? I think those are the only ones, right? So open set is just going to be the same thing we have for Q set. Basically, it is Dijkstra with a heuristic that improves the what to try next. Yep, I'm learning. Came from is going to be an empty map, but what are we going to put into came from? Because we need to know what type it is. It's going to have a neighbor, so it's going to be the same thing, right? It's just going to take current. Oh no, it's going to be this prev thing. And that's not an equal sign. That should be a colon. This is came from. Except it's going to be not an option because we're only going to put things in there that exist, right? It starts as an empty map, and then we'll insert things into it. Okay, then G-score is a map with default value of infinity. Which is going to be I32, I32, usize, and we can set that to usize max. And then F-score is going to be a map with default value infinity, so same thing. Okay, so I think that's the whole thing. And then what we'll do is say A star is build part 2, and build part 2 is going to return us an A star instead of a Dijkstra. Okay, so let's split this up so I can see exactly what I'm looking at here. So we need an open set. We need a came from, and we need F score and a G score. And both of those start out, oh, just it's infinities and then the heuristic. Okay. So this is G score and F score. And now what we're going to do is in here, we still calculate these values, correct? Yes, but we're going to do an insert. And came from, sorry, is an empty map. So we don't have to do anything with that yet. Open set just has the start. So, whoops. Deleted everything. Open set just has the start. So open set, insert, 0.0. Oh, and that's all it contains. It just contains the node. It doesn't contain any value. So it truly is a set. What do we need? Yeah. Okay, yeah, so it's just a set. Like that. So we're just going to insert the starting position there. Okay, so that's that part of that. Came from is an empty map. We got that. Let's put these together so we can do these one at a time through the A star algorithm. And then F score. So G score gets set to everything is infinity except for the starting location, which is 0. And that's going to have to be done in here. And then, so yeah, we'll do a G score get mute 0.0 unwrap equals 0. So that's the G score setting to 0, starting to 0. And the F score has to be this heuristic. So F score get mute from 0.0 unwrap. I guess we can make it, I don't know, what would be a good number here? And we're estimating, right? We say width 9 times width plus height. I have no idea what to put there. And then we're going to build an A star with a width and height. And then we're going to do the open set came from G score and F score. Okay, and now we just need to set those up. So our, let me flip back here again. G score and F score are all infinity and came from is empty. So all we're doing is setting up. So where do we put the nodes? How do we find the neighbors? We need to create a neighbors map and see what, and they have a, this D I think is the cost of getting from current to neighbor, right? Modprog says, I would love to tinker with your code if you're not able to finish it. Okay, well definitely. If I as soon as I run out of time, I'll push this up onto GitHub. I have it over here. I'll paste my paste a link to my the repo for it. Where is it? AOC. There we go. There it is. Thank you, Modprog. Because I'm sure you're looking at this and saying, no, don't do it that way. Don't do it this way. And all I can do is apologize for that. So D, it should say D. D is the weight of the edge from the current to the neighbor. Right, so that's what we're going to store inside. Oops, not there, over here. What we're going to store here is we call it QSet in Dijkstra. We're going to call it, I just want to make sure, am I in the right function? Yes, build part 2. I'm going to call it the cost. And we're going to add that as a cost. And this is a hash set. Oops. Like that. So we're going to insert the cost to get from X to Y. And we're also going to, while we're doing this, we're going to set the G-score insert XPOS YPOS is going to be equal to the like this, the max. And we'll do that for F-score as well. We don't need prev, and then this calculates the value. Stop that. You don't know what you're doing or saying? You're leading me down the wrong path, Mod. This is all your fault? Okay, is this, no, that's still running. I'm gonna let it keep running for a while. All right, so this should set up our A star, right? And then what we need to do, we can't use a Dijkstra search, we have to use an A star search for part 2. And then if that works, we'll switch part 1 to use the A star search as well. Okay, so let's make the window big and then start writing our A star search. A star, and A star, and it returns a usize. Okay, so this shouldn't be too bad. Open set gets start, and so that's already been done. We did that when we built our A star struct. Came from as an empty map. That's done. G-score start. Yep. Okay, so we've done all this. So we're already down to here. We're halfway through this function. All right, so we just need to implement this part. While open set is not empty, current is equal to the node in open set having the lowest F-score value. Now, how did we do that in here? Yeah, we just looped over for k in A star open set keys. And then we're going to look at F-score. So we're going to grab smallest. And the found one. And then we're going to say the same thing here. If, we're going to, so you let F score is equal to F self dot, not self, A star dot F score get K. Oh no, we didn't have to do that. Just regular K, unwrap. And we put a star in front of that. And it gets us our F-score value. And we say if F-score is less than smallest, then F-score equals smallest. Oh no, smallest, sorry. Is F-score, and then found equals star K. All right, so that should be this first part here. And then we say if current equals goal, then reconstruct the path. Mod product says, as heuristic, use 1 star Manhattan distance. I think you are not allowed to overestimate an A star. Oh. Okay, thank you. Underestimation is better than overestimation. Got it. So there we go. That's our heuristic. Oops. I did a check instead, and now it's not working. Not found in the scope. Let. All right. Oh, cost. Oh, this is. Oh yeah, I never created a cost thing. Let's do that real quick. I do have cost there. It's just this. Let me grab that real quick and put it up here. Let mod cost. This is a hash map of that. It's hash map new. Inform. This should be came from. Oh, and then I missed open A star. I forgot to put cost in here and didn't complain. Maybe it was about to. Oh, can we iterate over it then? Oh yeah, and then we're not returning use size. Okay. Still not good. Oh, expected use, okay. As use size. Let's see, what do we have? Open set, cost, came from. It says expected tuple found option. Oh, did I leave the sum in there? Yeah, okay. I should have made these defined types instead. Okay, so that checks. We have warnings, but that's probably because we're not, there's a bunch of stuff we're not doing. All right. So we did the first part of this algorithm here. We found the current node, and now we're going to say if we hit the goal, oh, wait, this should be inside a while open set is not empty. And I forgot to add that. So let's shift everything over and say while A star, not A star, open set is empty. Do this. Okay. So now if found, and we're looking for the width and height, right? So it's the same thing we did down here, except we're going to call it A star instead of DI. Then we're done. What do we have in terms of? So how do we print out? So we reconstruct path came from and current. And that's the node with the lowest F-score value. So we actually have to work our way backwards. Okay. All right, so what we'll do is we'll break out at that point, and then we won't have found, but we can set, right, because we need to get came from and current is what I'm calling found. So we need to break out of that. I think you can say break found like that, and then say let current equals binary heap. Oh, is this a better way to do it, ModProg? As an optimization, let's pull that up. Oh. Oh, okay. I was not aware of this binary heap thing. Sand collections binary heap. Okay. A priority queue implemented with a binary heap. It'll be a max heap, but we can use a min heap if we do it this way. If we wrap it in reverse. Gives you the minimal value in O of 1. Yeah, so that's probably where a lot of my time is being taken, is doing this search. And we're going to take another quick peek here. No, it's still running. Okay, so we probably need to do that as well. Let me get it working first, and then we can make that optimization. I have maybe, I'm pushing it, but I have maybe another 15 minutes. All right, so if we found our thing, then we're going to break out at found, and then that current will be what we found. Do that. And then came from should be a list of all of what we found. So the first thing we do, or the next thing we do, sorry, is open set remove. Right, so that's similar to the Dijkstra again. Self, not self, A star. open set remove found. And then after that, we're going to go to each neighbor. And we're going to calculate a tentative score being the g-score of the current, which is infinity. Oh, no. Current is going to be start, so it's going to be 0. Plus the cost. And if the tentative g-score is less than the g-score of our neighbor, which it will be, then came from his neighbor. Okay. So let me just copy this over, because we can just put that right in here. That was, what a wonderful paste that was. Okay, so let's just do this and implement it. And I'm gonna cheat also by holding or keeping up Dijkstra, because a lot of this code is similar. So, oh, I missed out this line here for each neighbor of current. All right. This is looking worse and worse. For d endures, we're going to say let v, neighbor, let's call it neighbor since we'll use the same terminology, found.0 plus d.0, comma, found.1 plus d.1. And then we're going to say let tentative equals a star dot g score of current, which is what I'm calling found, unwrap, plus a star dot cost of found, unwrap. Right? Is that the way we do that? And what did I break here? Oh. Now I have an unclosed, oh, because I forgot to, I didn't close up my durs here. Let's do that real quick. So I just want to see if I got that right. No, that's wrong. You can't break with a value in a while loop. Oh, I thought you could. All right, we'll have to figure that out. Let mod current equals none. So we'll say current equals sum found, and then just break. Maybe you can only break out of infinite loops with that. And yeah, so this is where I was going to go for help remove the arguments. No method named, oh, it's gscore.get and cost.get. Okay, that's better. But maybe first get it running with the example and then do the optimization. Yeah, I agree. Okay, so what's next? If tentative is less than a star of a star g score get neighbor unwrap, then we're going to say a star dot came from insert neighbor and current. What's current found? This is bad that I didn't use the same name. And then a star g score get mute neighbor. Oh, I probably have to ampersand that. Unwrap equals tentative, and a star f score is tentative plus our heuristic of the neighbor. So our heuristic of the neighbor is going to be the Manhattan distance, which is going to be a star width minus found dot, it's neighbor dot 0 this down here so I can read it, and then plus a star dot height minus neighbor dot 1. Okay. If neighbor is not in open set, then add it. If, oh, we can just add it. Oh, a star, we don't have to check. Insert neighbor. Is that it? That's the whole thing. Don't need a semicolon there anymore. Okay. So is this is something. And all I'm doing right now is just printing a current and returning 0. Let's find out what doesn't check. Expected U size, found U size. So we do a star there. This has to be a star and a star there. Oh, and these are I32s as U size. And we can't insert. Oh, A star open set insert. Oh, I guess we don't ampersand that one. Okay, so that checks with warnings. So it came from is supposed to start empty, an empty map. Okay, so when we initialize it, it doesn't have to be mutable. Because we actually don't use it anywhere. We just can put it down here just to make the, okay. So I'm going to run this with the test data and see what, so current or found, this should just give us, it's a 10 by 10 5 times. So it should give us 49 comma 49 if we found a path. Oh, shoot, did I forget to change this? I did. And it panicked. Option unwrap on a null, none value, line 65. Oh, okay, so we need to check. We have to say if A star G score get contains key neighbor. If it doesn't contain the key, or that. There, okay, let's try that. I'm running it out here so I can hit control. Oh no, it's still line 68. Oh, get mute. Can I do entry or default? Let's do that. And now it doesn't like those. Okay. Unwrap or. Oh, unwrap or. Okay. 64. Yeah, we want unwrap or max, right? But I thought I inserted all of the G scores. They should all exist, right? When down here, when we did this, all our X pauses and Y pauses should exist. The G scores should exist. So I shouldn't have to do any of this. Oh, you know what I'm doing? I'm not doing is I'm not checking to see if we're in range. That's been the bug all along. We could be going off the map here, and that's probably what's happening. If neighbor dot 0 is less than 0, or neighbor dot 1 is less than 0, or neighbor dot 0 is greater than a star width minus 1, or neighbor. I mean, we should be able to do it using the, yeah, use unwrap or anyway, right? Yeah, that way we can just check. Unwrap. But we don't actually want to go into those locations. We don't want to actually go into those locations. One is greater than a star dot height minus 1. Continue. Okay. That checks. I have both things. I know. I gotta clean that up. All right. Day 15 part 2. So this printed out some 4949. Okay, so that means for part 2 that worked. It got an answer. I don't know if we got 315, and we need to figure out now how to go from current back to, and that's where this came from thing comes into play, right? So our total path is equal to our current, which is going to be our final location. And then while current is in came from dot keys, current equals came from current and total path prepend current, and then we'll get the cost. So total path should just be the cost. Let's use that as the cost. So let's do this, reconstruct path, because we don't need the actual path. We just need the cost of the path. Oops. Like that. You don't store the current cost in G. Oh, maybe. Yeah, if it's there. If it's in G-score. See, this is why I'm not familiar with this algorithm, but this is how I learn. A star G-score get current unwrap. Oh, didn't like that. Gotta ampersand it. Expected tuple found enum option. Oh! If let some current equals current. I guess I could say current to unwrap. There. Well, it got 307, so we're off by a little bit. It should be 315. Did we not add in the cost of the final step? Cost 307 to 315. That's 8. The cost of 8 is missing. Let me also print Lin the came froms. Oh, that's gonna be big. That's gonna be everything, right? It's gonna be everything we came from instead of current is goal. Yeah, maybe we need to add in that last one, but that's gonna add 9 instead of 8, so we'll be off by 1. Oh, maybe because we're adding the first one. Didn't they say don't include the first one? Yeah, I think I must have added the because the algorithm adds the first one, right? Where does it say don't add the first one? Don't count the risk level of your starting position unless you enter it. Okay, so that must be what we're doing, and I don't think I. Oh, did I mess up my? Oh yeah, this is the whole thing is a string now. Okay. Do I add? No, I have G score starts at 0. So we must be throwing that in there, right? So what we should be doing is returning A star G score get current unwrap plus our the cost to get to current. Oh, maybe that's what we need to do here. It's just set the G score. This will be easier. I'll just add it in here. A star cost get current unwrap minus A star cost get 0, 0. This is so hacky. Unwrap. And let's just return that. And if that fails, we'll just return 0 here. That checks. That runs. And we get 315. So we forced it to work. Okay, so now let's try it on the real input. Is this done yet? Nope, still running. Okay. And let's see if A star works any better with, oh yeah, then we have to do the optimization. That might blow up. This might blow up the thing I have running in the background because I'm overwriting the binary. Come on, you can do it. Yeah, maybe I need to do that binary thing now. Oh, it did it! 29.95. Is that the right answer? Holy crap, that's right. Thank you, ModProg, for all your help, and thank you everybody who's watching for your moral support. Seeing you here is enough. You don't have to chat if you don't want to. That was pretty good. Okay, so the next thing to do would be to optimize this part. Use a binary heap to find min instead of this mess. What I'm going to do, since I am totally out of time, thank you, General Nova. General Nova says, woo! Thank you, General Nova. Okay, so that was good. What I'm going to do is I'm going to check this in. Let me delete all these extra extraneous comments and whatnot. Yeah, there's another one right on here. And then we can clean this up in ModProg. You can have at it, send PRs. I'd be happy to take them. Let's get Clippy to be happy as well before I take off. Hey, listen. You told me to use into iter before. Call directly iter. Okay, 125 and 155. Okay, and 155. Like that. That should still check. Good. Clippy should be happy. And then if I run this again, I'm gonna finally kill that. Cargo run release. I don't want to even guess about how long it would take to run this in debug mode. Sometimes it really helps explaining things to understand these things better yourself. I totally agree, ModProg. There's so many times that I've learned in front of my colleagues just by talking about what I'm working on. Okay, so those answers are still the same. Clippy's good, and we're gonna git add source. That's up here, right? Yeah, git commit -m day 15 part 2 unoptimized solution, and we will push that. And we'll call a stream. And what we can do, if there's another day that goes quickly, like yesterday went really quickly, we can come back and binary heap that thing. Or ModProg, if you're interested, feel free. I'm more than happy, like I said, to accept PRs against this. That would be cool. Okay, let's see. Is there anybody streaming that we can go raid? Because I'm way over my limit on time. There's nobody to raid. That's sad. Okay, that would have been fun. I had fun anyway doing this. Thanks again, everyone, for watching. And I will see you tomorrow for day 16. Take care. Okay, back real quick. ModProg says he's going to stream in 2 minutes, so let's go make sure I'm following him. I should be following, or them. Sorry, I apologize. I shouldn't assume. Yes, following. Okay, so I'll hang out for 2 minutes. ModProg will get there. Oops. ModProg will get their stream going, and then we'll go raid them. That'll be fun. Okay. Meanwhile, what can we do? We can look at leaderboards. Let's go do that. Personal stats. Okay, so that took an hour and 10 minutes to get part 2 done. Mostly because I never implemented A* before. That was cool. The previous one was an hour to get from, day 8 took an hour. Okay, and what other leaderboards am I on here? Private leaderboard. Sam. Oh, I'm in 3rd place now. Chael. I am down in 10th. That's sad. Togglebit in 8th. And I was just checking to see if OnProg was up. Prime, where am I? Way down, 32nd. And then, oh, okay, good. He did yesterday's. You are now up. Okay, let us go raid ModProg. Why is it not showing up on my raids? I am following. Oh, I can just type it in, right? ModProg. Oh, it's not showing up. Oh, I don't know. I thought I could. Why is it not letting me raid you? I'm going to pause my music and then so I can hear you. Okay, I'm refreshing. Oh, there you are. I see you. Yeah. All right, we're ready. And we're going to raid now. Okay, see you in a second.